Welcome to lesson 4.3. We are moving along. This lesson is all about periodic trends. And so we're going to talk about a couple of different things. There's probably going to be a couple of different videos to watch. So I'll try to make them a little shorter. So the first thing we want to talk about is ionization energy. And I'm going to scooch down a little bit and define it right here. But ionization energy is the energy required to remove an electron from an atom or an ion. Remember, we talked about in the last lesson how those groups 1 and 2, especially with their low number of valence electrons, it was much easier to remove an electron from them than it is from, say, something in the group 17 or 18 or 16 even, that have the more valence electrons. Here's a little example up here. You see we have a neutral aluminum atom. It's got 13 protons. So neutral means it has 13 electrons. There are 2 in this first energy level, 8 in the second energy level for a total of 10, and then 3 more in that third energy level for a total of 13. So when an electron is removed, some ionization energy is required to remove that electron. It's because it's attracted to the positive, but remember, because it's further away, sometimes it's easier to remove them. And then when that happens, you remove that electron, just like we talked about in the last lesson. You have an ion with a positive 1 charge. Because now you can count them. I only have 12 electrons. 2 here, 8 here for a total of 10, and then now just 2 more in the outer shell. 13 protons, 12 electrons means I have a positive charge. So the ionization energy, just some trends about it, it increases as you go along the periodic table from left to right. So it increases as the number of protons increase. It increases as the number of protons increase in the same row or period. Okay? So this is because as the number of protons increase, they attract them greater, more strongly. I guess is a good way to put that. So more protons means more positive charge, and so they're going to pull stronger on the electrons because there's more of them, right? And so that means that they are more strongly bound together as you go across the level from left to right. Okay? More protons, stronger pull. So as you go from left to right, that energy is going to increase. And you can see that happening here. Here's just the numbers that represent that energy. 520, almost 900. This is a little bit of a abnormal one, but that happens. 1,000, 1,400. But generally, you can see they increase from 500 up to 2,000. Now, the other trend that happens with ionization energy is it decreases as you go down a column, down a group. And that is because as the energy level increases, energy levels increase. So you're getting more and more energy levels. The inner electrons block, well, let's say shield. I like that better. They shield the outer electrons from that nucleus. So they interfere with that positive charge. So they're kind of blocking it. Also, the valence electron, so they interfere with the nucleuses. I should just stick with what I'm doing and not go off on a tangent. With the nucleus's attraction to the valence electrons. And as I was going to say, also, as you're adding more energy levels, the outer one gets further and further away. All right? Let's say it gets larger and farther away. So as you increase those levels, just to use this as an example, you see this third level, this third circle is bigger than the first one, and it's also further from the nucleus. Excuse me. So because of that, this ionization energy as you go down this group gets smaller. See, it's 1300. When you get to the bottom, it's down to 380. So you can see just a general trend. It's not going to apply 100% every time, but generally as a trend, when you go down the group, it's getting lower because these valence electrons are further away from the positive charge. So we'll write that down. I just said it. So this causes the elements further down within the same group to have lower ionization energies. The valence electron is easier to remove when it's farther away. So it's easier to remove that electron. So here, back in my aluminum example, it's a whole lot easier to remove this electron than it is to remove this one because it's further away. So that general trend, as you get bigger and bigger atoms, the outer valence electrons are further away, so they're easier to remove.